Alright, so in this problem, I have a to the power of x plus 2 to the power of x is equal to 130. So I'm going to first start by rewriting 8 as 2 to the power of 3. So I get 2 to the power of 3 to the power of x plus 2 to the power of x is equal to 130. Now, if I have something in the form a to the power of m to the power of n, this is equal to a to the power of n to the power of m. So these two are the same thing, meaning 2 to the power of 3 to the power of x. I can rewrite that as 2 to the power of x to the power of 3. And now I have this plus 2 to the power of x is equal to 130. Now I'm going to let 2 to the power of x equal to y. So now I have y to the power of 3 plus y is equal to 130. And if I subtract 130 on both sides, these two cancel out, and I get y to the power of 3 plus y minus 130 is equal to 0. Now 130 is the same thing as 26 times 5. So I'm going to rewrite this as y to the power of 3 minus 25y plus 26y minus 130 is equal to 0, because 5 squared is 25, and 26 goes over here, and negative 25y plus 26y is equal to y. Now, this gets me to factoring out by grouping. So I'm going to group y to the power of 3 minus 25y and 26y minus 130. So for y to the power of 3 minus 25y, the greatest common factor is y. So I get y times y squared minus 25. Plus, from 26y minus 130, I get 26 times y minus 5. Now, if I have something in the form a squared minus b squared, this is equal to a plus b times a minus b. So y squared minus 25, that's the same thing as y squared minus 5 squared, which is going to equal y plus 5 times y minus 5. So I get y times y plus 5 times y minus 5 plus 26 times y minus 5 is equal to 0. And now if I factor out y minus 5, I get y minus 5 times y plus 5 plus 26 is equal to 0. And this gets me to y minus 5 times y squared plus 5y plus 26 is equal to 0. Now from here, this gives me two equations. I get y minus 5 is equal to 0, and I also have y squared plus 5y plus 26 is equal to 0. So for y minus 5 equals 0, this is simple. All I have to do is add 5 on both sides, and I get y equals 5. Now for y squared plus 5y plus 26 equals 0, I'm going to have to use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac over 2a. So in this case, a is 1, b is 5, and c is 26. So I get y is equal to negative 5 plus or minus the square root of 5 squared, which is 25, minus 4 times a, which is 1, times c, which is 26, all over 2a, so 2 times 1. And now this is equal to negative 5 plus or minus the square root of 25 minus 26 times 4, which is 104, all over 2 times 1, which is 2. And now this is equal to negative 5 plus or minus the square root of negative 79 over 2. Now, you can't take the square root of a negative number, so this is no solution. So I'm simply left with y equals 5. And now remember how we let 2 to the power of x equal y. So this means that 2 to the power of x is equal to 5. Now to solve this equation, I'm going to take the log on both sides. So I get log 2 to the power of x is equal to log 5. And if I have something in the form log a to the power of b, I can move this exponent b to the front, so it's going to equal b times log a. So in this case, I have log 2 to the power of x, and I can move x to the front. So I get x times log 2 is equal to log 5. Now if I divide both sides by log 2, these two cancel out, and I get x is equal to log 5 over log 2. And I can just rewrite this as log base 2 of 5. These two are the same thing. Alright, so in this equation, I have 1 to the power of x is equal to 3. So this might seem like an impossible equation, right? Because how can 1 be to the power of any number and equal to 3 if 1 to the power of even a million is still equal to 1? Well, let's try to solve this equation the way we would solve any other exponential equation. The first thing I would do is take the natural log or ln on both sides. So I get ln 1 to the power of x is equal to ln 3. Now, if I have something in the form ln a to the power of b, I can move this exponent b to the front, so this is going to equal b times ln a. In this case, I have ln 1 to the power of x, and I can move x to the front. So now I get x times ln 1 is equal to ln 3. And now if I divide both sides by ln 1, these two cancel out, and I get x is equal to ln 3 over ln 1. Now, if you guys already didn't know, ln 1 is equal to 0. So I get x is equal to ln 3 over 0, and you can't take any number and divide it by 0 because that's undefined, meaning this has no solution. So that method doesn't work. However, this just means that there are no real solutions. But there are different types of solutions. So what I'm going to do to solve this equation is, first, let's recall Euler's formula. And if you guys don't know what this is, it states that if I have something in the form e to the power of I times theta, this is equal to cos of theta plus I times sine of theta. And I know this may seem a little complicated right now, but just bear with me. So let's say that theta here is equal to 0. So if theta equals 0, then I get e to the power of I times 0 is equal to cos of 0 plus I times sine of 0. So then I get e to the power of 0 is equal to 1, cos of 0 is 1, plus sine of 0 is 0, and 0 times I is 0. So 1 plus 0. And e to the power of 0 is 1, so I get 1 is equal to 1 plus 0. Now, what if we say that theta is equal to 2k pi? K being a constant, so it could equal any number, 1, 2, or 3. So if I plug this in, I get e to the power of I times 2k pi is equal to cos of 2k pi plus I times sine of 2k pi. Now, what if k is equal to 1? What if our constant k is equal to 1? Then I get e to the power of I times 2 pi is equal to cosine of 2 pi plus I times sine of 2 pi. Now, cosine of 2 pi is 1, and sine of 2 pi is 0. So I get this is equal to 1. Now, if k is equal to 2, I would get cos of 4 pi plus I of sine 4 pi. Cos of 4 pi is 1, and I times sine of 4 pi is again 0. And if I do the same thing with 3, I would again get 1 plus 0. So this pattern continues, and it keeps on equaling 1 no matter what value of k we get. So we can say that e to the power of I times 2k pi, this is equal to 1 no matter what value of k we have. So now this means that we can substitute this in back to our original equation, which is 1 to the power of x is equal to 3. This is our original equation, and we can substitute in 1 for e to the power of I times 2k pi. So now I get e to the power of I times 2k pi to the power of x is equal to 3, and this is my new equation. So now, to solve this, I'm going to do what I did at the start. I'm going to take the natural log or ln on both sides. So I get ln e to the power of I times 2k pi to the power of x is equal to ln of 3. Now, if I have something in the form ln a to the power of b, I can move this exponent b to the front, so I get b times ln a. In this case, I can move x to the front, so I get x times ln e to the power of I times 2k pi is equal to ln 3. Now I'm going to use this property again and move this to the front as well. So I get I times 2k pi times ln e is equal to ln 3. And ln and e, these two cancel out. So now I'm left with I times 2k pi is equal to ln 3. Sorry, and I also have x. Now I'm going to divide both sides by I times 2k pi. So when these cancel out, and I get x is equal to ln 3 over I times 2k pi. Now I'm going to multiply this by I over I, which is the same thing as 1. So I get x is equal to I times ln 3 over I times I squared, and if you guys already know, I squared is equal to negative 1, so over negative 2k pi. And k in this case can't equal 0, because if k were 0, this wouldn't work. So this is my solution to this equation.